Students, hi. So far we discussed about VSEPR theory and polarity of molecules. And today we are going to discuss about the VBT or valence bond theory. Okay. So why we are discussing valence bond theory? What is the problem with VSEPR theory? Let us see the limitations of VSEPR theory. It gives geometry of simple molecule only. That is the limitation of ESCPR theory. And it can't explain it in detail. Okay. So it is having limited applications. So we introduced a new theory. Who introduced? Hitler and London introduced in 1927. New theory that is called a valence bond theory. So if you discuss about valence bond theory, we have to discuss the concept of hydrogen bond. Okay. Suppose there are two hydrogen atom A and B. It is having nucleus Na and Nb, and it is having electron Ea and Ev respectively. Okay. So let us see what type of attractive forces are present inside that. Okay, if you have two atoms, two hydrogen atoms, if you have two hydrogen atoms, Ha and Hb. Okay, what are the nucleus is Na, and it has one electron. The electron is called Ee. And there is another nucleus Nb, and it is having an outer electron Eb. Okay, suppose they are approaching each other. When they are approaching each other, we already know that there is an attractive force between these two. One nucleus, the nucleus in Ha, and the electron present in Ha, right? So there will be an attraction between the nucleus and electron within each atom. So that is represented by this dotted line. Okay, this is all the force already existing inside each atom. Okay, the attraction between the nucleus and its electron. Now, when they are approaching, what will happen? There will be another sort of attraction also. This nucleus will attract the electron present in Hb. Okay, and this nucleus will attract the electron present in Ea. That is this new sort of attraction which is existing. So there are actually how many type of attraction? 4 type of attraction. When they are approaching, we can see 4 type of attraction. Okay. Now let us see what are the different type of repulsive force which is existing when they are approaching. So when they approach each other, you know that positive and positive will repel each other, right? So when they approach each other, these two nucleus will repel each other. Okay, the nucleus of the two hydrogen atom will repel each other. At the same time, the electron present in each atom will repel each other. So there are 2 type of repulsive force also existing between them. Okay, so now let us take a graphical representation of the approaching of hydrogen atom. So this is the graphical representation of approaching of hydrogen atom. So in this particular case, let's see, here they are far apart. Okay, the hydrogen atom is not near, they are far apart. Now, when you move from here, this is the potential energy. Y-axis give us the potential energy, and the x-axis will give us the internuclear distance. So when these atoms are approaching each other, when we are moving from here to here, that is when internuclear distance decrease, they approach each other. Okay, so when they are approaching each other, the attractive force is predominating. So we have discussed 4 type of attractive force. So that will be predominating when they are approaching each other. So what will happen? So the energy, that is the potential energy, is decreasing when they are approaching each other. And at a particular instant, what happen? Completely, the potential energy will reach to a minimum value. So the internuclear distance at that particular point, that is called the bond length. That is stable state. Okay, the stable state. So this much only this atom can come close together. If these atoms are come still close together, what will happen? The internuclear distance is going to decrease, and at the same time, the energy is increasing. What is the reason? Because if they still come close together after 74 picometer, again they are coming close together, the repulsive force will predominate there. Okay, which force will be predominating? Repulsive force. So at first, attractive force will be predominating, and we will reach to a minimum value of potential energy. So at that minimum value of potential energy, the internuclear distance is equal to the bond length. Okay, and after that, if they are still coming close together, the repulsive force predominate, and what will happen? The potential energy increases and the stability decreases. So this is the stable state. So when they come close together, the repulsive force is more, so energy increases and the stability decreases. That is what this graph is representing. Okay. So the magnitude of new attractive force is more than the new repulsive force. When here the attractive force is more than the repulsive force, and when they reached the minimum value, attractive force balance the repulsive force, and when they reach here, repulsive force predominate over the attractive force. That is happening in this particular graph. As a result, two atoms approach each other and potential energy decreases. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion. Okay, that is called, at that particular point, the internuclear distance is called the bond length. Okay, and the system acquire a minimum energy. Okay, next is when they approaching each other, actually this is having a high energy. These two atoms is having high energy. So when they approach each other, they are losing their energy, right? They are losing their energy. And when they reach here, they lost a lot of energy. Okay. So this energy which they are losing, that will equal to the bond energy. Here, that will be equal to the bond energy. So the energy that they are losing, these atoms are losing to get a stable configuration, that will be equal to its bond enthalpy. That is equal to 435.8 kilojoule per mole. Now let us see the concept of orbital overlap. So far we were discussing the same thing only in the case of hydrogen molecule. Okay, so hydrogen molecule formation we have discussed. Actually, two hydrogen atoms was approaching each other. When these two hydrogen atom approach each other, actually where is overlapping take place? 1s orbital. The electronic configuration is 1s1, outer electronic configuration. So actually these two 1s orbitals are overlapping and the electron pair up in between them. Okay, so partial merging of atomic orbital is called the overlapping of atom. This is the overlapping of atomic orbital. Greater the extent of overlap, the extent of overlap, okay, the extent of overlap, this is the extent of overlap. If it is greater, stronger will be the bond. Okay, when the orbital of two atoms come close to form bond, their overlap may be positive, negative, or zero. So the overlap we can divide into three, maybe positive or negative or zero. Let us see what is these three cases. Okay, so positive overlap. Positive overlap means that orbital forming bonds should have same sign and orientation in space. This is called a positive overlap. It's very clear. Look at this overlap. Here, two p-z orbitals are overlapping. We know that p orbital is having which shape? A dumbbell shape. It is having a dumbbell shape. Two lobes are there. One is positive, one is negative. So if two px orbitals are overlapping, if the positive parts are overlapping, then it is called in phase or positive overlap. Look at this 1s and pz orbital. Positive is overlapping. So it is positive overlap. Here are two positive overlap, okay, in the px cases. This is the case py. Along the y-axis, this positive and positive is overlapping. So these all are coming under positive overlap, okay. Now let us see what is negative overlap. Of course, it is opposite to this positive overlap. Here, opposite signs are overlapping. Okay, the lobes with the opposite signs are overlapping. Look at the same cases, but what is the difference? Plus and negative. Okay, positive and negative is overlapping. Here also negative and positive. Here also every case is positive. So that is called a negative overlapping. Now, what is zero overlap? Zero overlap means there should have no proper orientation of orbitals. So look at this case. The orientation is different because they are not close together. Okay, they are not overlapping here because the orientation is not proper. So such overlapping is called zero overlapping. In the case of zero overlapping, no overlapping is taking place. Okay, now let us see the nature of covalent bond. There are two types. Okay, sigma bond and pi bond. So now let us see in detail what is sigma bond and pi bond. Sigma bond means the type of covalent bond is formed by the end to end or head-on overlap. This is also called, and this will be along the internuclear axis, and this is also called a head-on overlap or axial overlap. Let us see the case, then we will understand. So look at this particular case. Here, two hydrogen atom we already discussed. It is having 1s1 electronic configuration. 1s1 is the outer orbital. And then this 1s will be overlapping with another 1s. Okay. And the electron will be pairing in between. This is called a SS. 1s orbital is overlapping with the another s orbital. So this is called a SS overlap. And in this case, 1s orbital, what is HF? HF, if you discuss about HF, H is having 1s1 electronic configuration, F is 9, so it is 1s2, 2s2, 2p5. 2p5 means how we can write the orbital overlapping, orbital electronic configuration 1, 2, 3, 4, 5. One empty p orbital is there, right? One empty p orbital. So this p orbital and this 1s orbital is overlapping. So that is called a sp overlap. Okay. The sigma bond formed from sp overlap. Now pp overlap is there. If you take the case of 2f 9, so we know that 1s2, 2s2, 2p5. So just like here, only one p orbital, empty p orbital, that two empty p orbital will combine together, and what will get pp overlapping, head-on overlapping. So ss, pp, and sp overlapping is possible in sigma bond. Okay, and now let us move to pi bond. What is pi bond? In the formation of pi bond, the atomic orbital overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. So the orbital formed due to that is called sideway overlapping. So this is the case. Let us see this case. In this case, what is happening? This is perpendicular. Overlapping is perpendicular to the internuclear axis. This type of overlapping, sideway overlapping. So what will happen? If it overlap like this, the extent of overlap will be very less, okay, compared to sigma bond, okay. Now, let us see the difference between the sigma bond and pi bond. What is the difference between sigma bond and pi bond? So it is formed by end-to-end overlapping. Already we discussed, this is a summary, okay. It is formed by the sideway overlapping of half-filled p orbitals, okay. Overlapping take place along its internuclear axis. Here overlapping take place perpendicular to the internuclear axis, okay. The extent of overlapping is large and bond formed is stronger. Here the extent of overlapping is small and the bond. So the extent of overlap depend upon the strength of the bond. So sigma bond is stronger than pi bond. What is the reason? Sigma bond, the extent of overlapping is more than in the case of pi bond. Okay. So that is all for today. So we will discuss the hybridization in next session. Okay.